to see so many people interested about how Uber is doing all the infrastructure changes to make it more scalable, smart, and adaptive. So I have two main agenda items for today's talk. First, discuss like how we have to make think about the infrastructure very differently than existing infrastructure has been. And when I talk about infrastructure, it means data infrastructure. It's the infrastructure that is powering all the AI, business analytics, how we have to think about that. The second thing is, then I want to show two case studies or like two projects we have done at Uber to make the infrastructure much more smart and dynamic. And then there are a few ongoing projects. I will quickly tell all of those. So first thing, Uber, it, it has been only 9 years Uber started, but in 9 years Uber has expanded to 6 continents and serving now more than 600 cities. What's amazing is its growth. So in 2015, December, we did 1 billion trips. In 2016, we added one more billion. So in 1 year, we added 1 billion more trips. And in 2017, we completed 5 billion. So in last 1 year, we added just 4 billion trips. So the growth is phenomenal. And there are almost 75 million active riders, monthly active riders. So it's huge platform and creates humongous challenges. But the interesting thing to note is how we do this. So there's like, it's a lot of data driven. And just to showcase you one example, we have these kind of charts where we determine where the demand will be happening, how much demand will be there. And if on top of that, we can see there's a lag. So when someone requests a Uber, after 5 minutes or 10 minutes, the Uber comes. So this is actual when the supply happens. So for most of these cases, we actually predict when how much demand will be there. So making sure that the driver or there are enough drivers available in that area, depending on the demand. And we constantly do this kind of demand prediction. Now, all this requires a huge infrastructure investment. I mean, so you're trying, with all these billions of trips, you're trying to find these meaningful, small pieces of information and make a decision based on that. So one of the challenges for the infrastructure is scalability. You want to be it scalable in terms of data because you're capturing so much data from sensors, trips, and other thing, and then trying to find these meaningful nuggets of information. But there's another important challenge. You cannot just wait for this discovery. You have to have this information quickly available as soon as possible. This can be irritating, so I will just move to stop the animation. But the key point is over here. Scalability in terms of data is one thing, which Hadoop Hive provides. But there's another aspect of infrastructure is throughput. You want to able to mine that information as quickly as possible, and that's another big aspect of infrastructure. So that's why you see Uber and like many big companies have this kind of complicated infrastructure setup. You have many different pieces of information. So, for example, there's all this real-time processing systems like Kafka, through which all the data goes into Hadoop, where you actually, if you try to put labels, this is over here, you provide scalability in terms of data. Hadoop can store large amount of data, and using Hive, you can process that in a scalable manner. But Hadoop doesn't provide that throughput. I mean, if you guys have run Hive queries, you can, it can take several minutes for the results to come back. And that's why after we create our model tables, we actually push aggregates and some raw information to warehouse, where this warehouse is actually Vertica, which provides us within a few seconds results. So P95, 95% of the queries get results back in 20 seconds, whereas in Hive, 95% of the queries take 3 to 4 minutes. And then there's Presto and Spark, which provide scalability but also speed, but not as good as Warehouse. So in case of Presto, we get query latency about 1 minute. And then finally, a lot of data scientists use Notebook, which is a Jupyter Python notebook, or ad hoc query systems. We have our internal querying system which can connect to several different databases and run queries against those databases. So those are like mostly for ease of use access. There's actually third aspect to infrastructure. So the problem now is we talked about scalability and throughput, but if there's a high throughput, for example, in case of Presto, the throughput was very high, and that's why the adoption in just 1 year went by grew by 3x. This creates a problem because as the adoption increases, your throughput goes down. Now it's not linear, but it's kind of inversely proportional to adoption, but for general, we can say your throughput will decrease. Now, how do you keep maintaining that throughput if you want to maintain the competitive edge? You make more infrastructure investment. You keep on adding more boxes, making your Presto cluster bigger and bigger. The question then to ask, is that efficient? Is it you're wisely utilizing your network resources? So that is the key question. So the way at Uber we are thinking about data infrastructure is around these three metrics: how scalable we are, what is the throughput, and how efficient we are. And you're trying to balance all the three parameters. You don't want to have a very big cluster of nodes and being not very efficient. So trying to balance these three is the most important aspect of today's infrastructure. And how you can do this? Now, in this room, we have heard AI term a lot of times, and we all know it means artificial intelligence. But the way at Uber we are thinking of AI is not artificial intelligence, but adaptive infrastructure. So it's using artificial intelligence and machine learning to build an adaptive infrastructure. Uh, to clarify the term more adaptive, over here we mean infrastructure that can actually adjust itself to the business needs. As the business demands, business changes, we add more services, it's becoming smarter and trying to optimize utilization. There are a lot of interesting examples of small things we are changing, but I would like to present two very interesting cases where it's creating huge impacts for Uber. So, but by the way, I mean, to help build this adaptive infrastructure, Uber has created a team. It's called IAS, Infrastructure Analytics and Science. This team works with a lot of verticals like Hive, Presto, and Vertica, and try to find opportunities where we can use machine learning, artificial intelligence to make it more smart. And the goal is to provide compute efficiency, storage efficiency, and also for resource planning. So here's one project that I would like to talk about how we are creating efficiency in our storage. So in the infrastructure diagram, I showed a warehouse, which is basically a Vertica cluster. So we have 6 different isolated Vertica clusters. And we have 6 because of the query volume. We get millions of queries on a daily basis. These are like from internal employees and city centers and everywhere. And to handle that volume of queries, we have 6 different clusters which are isolated. And we have a load balancer which distributes these queries across different clusters. Now, in order to handle all those queries, we are replicating the data across all the different clusters. So for each table, each piece of data, we have making 6 copies so that we can reroute a query from one cluster to another cluster without any drop rate. Now, that's, I mean, it's a 6. So if you have like, let's say 100 terabyte of data, your actual data is getting copied 6 times and you're creating 600 terabyte. And Vertica charges license fee is based on how much data you're storing. So we are paying for 600 terabyte. That's a lot of money you're paying just for the handling a large volume. So what we are doing is we develop this partially replicated cluster idea, where we look at the depending on the query pattern, we rather than copying all the tables to all the clusters, we determine what are the association between different tables and how popular a table is, and based on that we apply optimization algorithms to determine optimal placement of clusters. So different clusters will have different set of table. So here's an example how we do that. So you look at a simple query, like all the queries. So let's say query 1, it has a 3 table, A, B, C. So you know that in order to execute that query, all those 3 tables have to be in one cluster. So assuming we put all the 3 tables in cluster 1. In the second case, now we see A, C, E. These are the 3 tables you needed. Now, A is already there in cluster 1. So ideally, we could have A and C are both available in the same cluster. E is not there. So we can make a decision either to put C in cluster 1 or put all the 3 tables in cluster 2. This decision is based on like how much is the difference between different cluster sizes. That's one of the optimization you're trying to do, because you don't want very unbalanced clusters. But this is the general idea, and then you keep on looking the last few weeks of query pattern and dynamically changing the clusters. So what's interesting now with this whole idea is there's at any given point of time, no one knows what is the current setup apart from the machines. Every week the algorithm runs and keeps on moving the table from one location to another, and just dynamically adjusting to the requirement. And if it observes some unseen query patterns, so for some reason, let's say someone is querying table A and E, and if the 2 tables are not available in single cluster, it will automatically adjust itself. And in that particular case, the query will get affected. Runtime will be longer because now it's trying to move the data, but it will get served. And every time a query gets executed, it gets logged in the query logs. Sharding algorithm picks it in the next week's iteration. And then there's a data loader, because all the data is getting prepared in Hive. So data loader communicates with the sharding algorithm, determines where to place the data. This is incredible. I mean, it involved a lot of engineering. I mean, it was less, I mean, definitely data science played a big role over here because it enabled how to do it. But apart from that, it involved a lot of infrastructure changes as well. And in some ways, these infrastructure changes, but giving us a huge advantage. I mean, we are able to reduce our disk space consumption almost by 30 to 40%. So instead of paying, let's say, for 600 terabyte, now we are paying a license fee only for 300 or 400 terabyte. So that's a savings of millions of dollars over the contract of our Vertica. So that's one example of how we are able to make a huge impact. Here's another example. In this case, this was a simple change, and which is saving a lot of resources for us. So Presto is a very popular engine on Hadoop because it can work on Hive, Hadoop, HDFS, and it has a very good query throughput rate. But then there are few percentage of queries that actually fail. It can fail either because of user error, syntax error, but those they don't really take any resources. But there are other queries that run, they are perfectly fine as a syntax wise, but fail because of other reasons. For example, HDFS has a bad node which is causing access to certain files becoming an issue. Or there are some system constraints. For example, in you cannot have more than 10 GB of memory on a particular executor. You cannot request more than 10 GB. So if you see the resources, the plot is showing the percentage of vcore seconds that is consumed by different kinds of error. The top two are like system constraints, which are like vcore, exceeding vcore or exceeding time limit, and the other is exceeding memory limit. And then the third is user error. These are like random user errors, ETL join issues and other thing. But I've removed the y-axis, but this is almost like 15% of the cluster resources are wasted because of these system constrained errors. Um, but we thought of, okay, can we build a model to predict whether a query is likely to fail? So the idea is, as soon as query gets submitted to Presto, we run in a separate process trying to determine whether the query is likely to fail or not. And it's a two-phase evaluation. In phase one, we just take the raw query itself and try to predict whether the query is likely to fail because of the system constraint. And if it is likely to fail, then we run a more thorough evaluation. We basically then call Presto Engine, asking for the explain plan and constructing more features out of it, and then determining whether the query is likely to fail. And if the query is likely to fail, then we stop that query from running and actually highlight a message in our internal UI where people can run the Presto query, saying that the query is likely to fail, and that's why we are stopping the execution. And you can look at some more details over here. And by the advantage we get out of this is, not only we are saving almost like 15% of our cluster resources, but also there's another bad thing that happens when these queries are running. Because these queries exhaust cluster resources, you're creating a long queue of queries that are waiting for this query to fail after some time, and then they only get resources to get executed. So one way, you could have done is like, okay, get a bigger cluster, but even if you get bigger cluster, you still will have certain queries that are just exhausting all the resources. So this was another interesting project that is like didn't require a lot of engineering changes and can sit outside, but it's providing huge opportunity for improvements. Then there are a few other ongoing projects like Chargeback. This is also an interesting project. It's not so much machine learning or AI project, but it's more trying to accountability, and it's more related to analytics. The idea of Chargeback is you're generating tons of data for different projects. Let's say for one modeling project, I'm generating and creating data. And if I don't do a good job of cleaning my old data and creating duplicate copies, then we want to have some estimate of how much is the cost of keeping that data as compared to the value that you're bringing from the project, from that machine learning project. So for example, if I'm keeping last 2 years of data and for some recommendation engine, and instead of 2 years, I just use 1 year of data, and I can reduce my storage cost by, let's say, 50%. And the impact of that on the algorithm is only like 0.1%, or which is completely negligible. Then you can put a dollar value onto saying that by decreasing my accuracy by 0.1 or a negligible amount, but reducing my data from 2 years to 1 year, I can save this much dollar value. Also, Chargeback is interesting in a lot of cases because it's creating some kind of comparable measure for the teams to understand how much data they are generating, how much is the value of that data. Then we have some forecasting problems like doomsday. Doomsday is just trying to predict when our resources will get exhausted. So we can in advance make sure that we have enough resources available. Uh, and then self-serving infrastructure analytics board is trying to provide tools to the verticals like Hive, Vertica to understand what are the queries that are consuming resources, how they can optimize, and it's kind of surfacing interesting analytics reports on a periodically for them. Um, okay, I think just in time. Uh, Thank you.
Thank